My name is Crispian Morris, and I'm presenting our work ST-MFNet Mini, Knowledge Distillation Driven Frame Interpolation for ICIP 2023. Frame interpolation is a widely used technique for increasing the temporal resolution of video content. It can be used to create slow motion or fast motion effects, or to fill in missing frames in videos which have been corrupted or have dropped frames. In this work we present ST-MFNet Mini, a lightweight frame interpolation model, as well as our proposed workflow for compressing other large models. The proposed problem is simple. Given two existing frames in a video, we would like to reproduce the center frame. Current deep learning approaches work well for this task, but the best ones tend to be very large and often quite slow. Ideally, we would want improvements in learning approaches to this problem to increase in performance and speed while decreasing in size. Currently, the size and speed of the best existing models limit their applications greatly. Heavy VRAM requirements prohibit deployment on consumer hardware and in consumer software. They limit the speed at which interpolation can be done and stop new use cases from being found. So, how do we do this? The first approach we consider is knowledge distillation. Here, we use the output of the large and slow model referred to as the teacher to assist in training a new model, referred to as the student. The student model has the same functionality as the teacher, but with reduced model size as shown in the figure. The difficulty is only in obtaining the optimal structure for the student model. To overcome this, we propose to use model pruning, which identifies redundant layers and enables reduction in model size. We will use this to create the student architecture for knowledge distillation. As an overview, we start with a large, slow model, prune it using a state-of-the-art pruning optimizer, and use the outcome to shrink the original architecture, resulting in a student architecture for knowledge distillation. We then train the model using a novel distillation loss, which will result in an optimum compressed model. OBPROX-SG from Chen et al. Is a state-of-the-art stochastic method for solving the large-scale L1 regularization problem for inducing sparsity. It takes the general form here, where lambda is a constant greater than 0 which controls the level of sparsity in the solutions, and f of x is the loss function to be minimized. We choose the Charbonnier loss as this function, shown here for completeness. We train using this optimizer for 20 epochs or until the density is sufficiently low, as shown in this graph. Once the model density is low enough, we can examine the density of individual layers in the network and use these as the compression ratios for each layer. We calculate the individual density as the number of weights greater than 0 divided by PL, the total number of parameters in each layer. We then use each value as the compression ratio for the respective layer, assuming that the density correlates with the size that layer should take up. We then iteratively form new layers, shown here as L', starting from the output layer. For example, if the densities for the last two layers in a network were both 0.5, we would set the compression ratios for those layers as 0.5. If the following layers were the dimensions associated, they would produce the following output. We follow this process for every layer in the original ST-MFNet, except the first, where we leave the input channel's value intact. After this, we have obtained a compressed architecture. Compressed architecture, it's worth noting some aspects of the originals. The original model contains several separate components, most of which were beneficial to the excellent overall performance of ST-MFNet. Viewers are referred to the original paper for details on these components. However, after our pruning is complete, we observe that the BLFNet, a component of ST-MFNet which helps to deal with large motions, is found by the optimizer to contribute extremely little to the overall performance of the model. After publication, it was found that scenes with large motion did not appear in our training set to the necessary extent, which explains why the optimizer found BLFNet to be redundant. We recommend that the dataset used for pruning be representative of the test sets in future. Otherwise, our shown reduced architecture achieves a 91% reduction in parameters from 21 million to just 1.8, as shown. We initially train a baseline student model without any knowledge distillation to determine whether or not the distillation loss actually provides a benefit or not. Here we use the Laplacian pyramid loss. The model performs to expectations, performing similarly to the teacher model in several test sets, and even outperforming it in others. Next, we train the student architecture using a distillation loss term, where the output from the teacher is also taken into account. Comparing the distilled model to the baseline, we can see that the distillation loss improves the scores of the model in every test set, showing that the knowledge of the teacher has in fact been received by the student. Numerically, we compare both the baseline and distilled models to the original and other state-of-the-art frame interpolation models. The distilled model performs very competitively given its minuscule size. A failure case is evident in the Davis test sets, though, where our approaches fail to compete with other models. This is mainly due to the large dynamic motion present in this test set and our model's inability to deal with it due to the removal of the BLF-net. Here we show the mean PSNR values of all tested VFI approaches against their model parameters and against their runtimes. It can be observed that ST-MFNet Mini, trained with knowledge distillation, achieves an excellent trade-off between performance and model size, with the lowest model size and second best overall performance. The model with the second fewest model parameters, CDFI, is nearly 3 times as large, and the only model which outperforms ST-MFNet Mini is its teacher, ST-MFNet. However, while the compressed model outperforms greatly for its size, it does not meet the same expectations for its runtime. Despite being 35% faster than the original ST-MFNet, the model is still significantly slower than other, larger models. This is most likely due to the upscaling components of ST-MFNet, the 3D CNN, which requires lengthy computation time. This will be a focus of future work. Here we show outputs from our distilled model compared with the original and ground truth. Whilst not perfect, our distilled model produces frames closely resembling the ground truth and very difficult to distinguish from that of the original model. In conclusion, we present an easily implementable method for simultaneously reducing an existing model's size and increasing its speed. It requires little knowledge of the specifics of the components in the model and can even improve upon it after training and without additional components. In future, we will attempt feature-based or other forms of knowledge distillation, establish the transferability of our workflow to other deep learning approaches, and try to improve upon the speed increase. Thank you very much.